Hello there. Now we are trying to resolve the few numericals on the distributed load. As we know that the distributed load is nothing but that is going to be spreaded over the length or area or the volume of the member. So then how it is going to be exerting on that member and what type of the reaction forces are going to be generating. Already we do have seen the reaction forces are generating on the basis of the type of the supports. Now that is the problem what we are going to be discussing here, the distributed load here. That's going to be a beam. Now the member we do have taken the a beam supports a distributed loads. So in this case what will happen, that beam is going to be supports the distributed load as shown in figure. So that's figure I had given over here. That's going to be a B is going to be your the beam ends, and here one end of the beam is going to be given the triangle and another is going to be the roller supports we do have given. So then in this case what will happen, this is going to be the distributed load is going to be spreaded. At A it is going to be 0. When it comes to B, it has the load of W that's going to be existed in terms of the Newton meter. So what the determine the resultant of the distributed load. So this is the distributed load. We need to be find out the resultant force, and next the reactions at the supports A and the B. So that's we need to be find out in this case. The two parameters we need to be determined. First we need to convert this into a point load. That's going to be a single concentrated force that we have to take it. So now the first parameter we are trying to find out here, the resultant of the distributed load. So how we are going to be calculating the resultant of the distributed load? That means the resultant of the distributed load here is going to be the single concentrated load we are going to be converting from the distributed load. So that's how it is going to be. The area under the load curve is the resultant of the distributed load. That means area under the load curve means this is going to be the area under the load curve. So that's the area we need to be find out. So as we know that the area under this load curve is going to be what kind of shape it is going to be representing. There we can see it is going to be representing the like a triangle. So there we can see A, B, C. If I am going to be give the notations, so then what will happen? It is representing the triangle. So now the area under the load curve. So area of the under the load curve is going to be, that's going to be area of A, B, C is going to be, I'm going to be considering here. That is going to be your distributed load. So that is equal to, what is the formula we do have? So that's going to be area of the triangle is going to be half B into H we are going to be considering in terms of the geometrical properties. That's the same that I'm going to be giving here. So this is in terms of the geometrical properties. But in this case, what will happen? This is going to be existed in terms of the load as well as the length. This is the combination it is going to be available. So that the same I'm going to be taking over here. That's going to be half. And here is going to be the B. I'm going to be taking the W. That's the load is going to be acting. And this is going to be the length of the beam I have taken. So that's the same geometrical properties of the triangle I have converted into the load as well as the length parameters. Now, when I'm going to be substituting in this equation, I'm going to be getting the resultant of the distributed load. So, the resultant of the distributed load, I'm going to be representing with the capital W. So, that's going to be capital W is nothing but already we told that is going to be the point load, that is in terms of the newtons. So, that's going to be half. The B is going to be, here is the W. That's going to be W is equal to 2000 newtons meter. So that's into L is going to be the 3 meters we do have. So then finally, when I'm going to be simplifying this equation, I'm going to be getting around, this is going to be 1000 times. This is going to be 3. That's going to be 3000 newtons. I got it. So that is equal to capital W. So that means the total load, the distributed load is converted into a resultant load. And here, the graphically I was represented here, that is going to be the distributed load is converting into the point load. That is going to be the AB beam with the 3 meters length. That's W is equal to 3000 newtons. Now, we need to find out the location at exactly it is going to be located. It means that from A, what is the distance it is going to be located? That's I'm going to be say the XC. So then how could you find out the XC? That means the location of the point load on the beam. So for this one, we are going to be applying that the theorem of Verignan equations. That's going to be the load moment of inertia we are going to be applying. So that I'm going to be taking over here. So that's already we do have. So that's going to be W into XC I am taking, that is equal to, so that's going to be your W into. So here, rather than taking this one, we are trying to find out the centroid of this triangle. Then already we have discussed about the centroid of this triangle. What is the centroid of this triangle? Centroid of triangle. Because the distributed load is going to be existed in that part. With respect to A, if I am going to be taking, that's going to be XC is going to be, that's we are finding, the centroid is equal to 2h by 3 we are going to be taking here. The h is nothing but is the length of this member, that's going to be 2l by 3. If I am going to be substituting in this equation, so that I am going to be getting the 2 meters from here, that XC is equal to 2 meters. So that means the resultant is going to be the 3000 newtons is going to be acting. At the same time, it is from A, it is going to be the 2 meters. From B, it is going to be the 1 meter distance it is going to be existed. And this way, we have calculated the resultant of the distributed load. Now, we are going to be calculating the reactions of the supports A and B. So, from this one, I am going to be removing all these supports to find out the reactions at the supports. So, the same diagram I am going to be representing with the skeleton here. With respect to this is going to be your RA and this is going to be your RB. And the load is going to be acting 3000 newtons, that is after converting into the distributed load, and that means it is at a distance of 2 meters and this is going to be totally a 3 meters distance we do have. So from this one it is going to be very easy. So once it is there, then I am applying the equations of equilibrium. So that's going to be sigma f of y is equal to 0, because can you see the two forces are acting in the vertically, one force is going to acting in the downward direction. That's going to be RA plus RB is equal to 3000 newtons. Alright, the 3000 newtons, this is the equation 1 if I am going to say. In the single equation 2 unknowns it is difficult, then I am going to be taking the moments at A is equal to 0. So when I am going to be taking the moments at A is equal to 0, then RA with respect to the moments with respect to RA will going to be 0. But RB at a distance of 3 meters, this is at the 3 meters. One is going to be acting in the clockwise direction, one is going to be in the anti-clockwise direction. So I am going to be taking anti-clockwise direction is the positive. Now the clockwise I am considering as the negative. Right? So in this basis, I am going to be writing RB into the distance is going to be the 3 meters distance, that is equal to 3000, that's going to be the load, and into the 2 meters we are going to be considering. So after the simplification, RB is equal to, we are getting 2000 newtons we are getting. Right? So RB is equal to 2000 newtons. If I am going to be substituting in the equation 1, then RA is equal to what will happen? This is going to be RB is equal to 2000 newtons, 3000. 3000 minus 2000, then RA is equal to, I am getting the 1000 newtons. So this way we are going to be calculating the reactions.